We all know a quote that the journey of 1,000 miles begins with only one step. We all already taken that first step. So now let's proceed to the session. So for this session, firstly we are going to learn about basic electronic tools. But I hope you already get the module. So in the module, you can see for the tools there are tweezers, diagonal cutter, crimping tools, oil stripper, long nose peelers. There is nothing much to teach you about these tools. You can just see and you will know what to do with this. But for soldering iron and multimeter, we are going to have fun. Let us watch some videos together.
If you do any work with electronics, soldering is one of the most valuable skills you can learn. From circuit components to wire splices, soldering allows you to join any two components together with a strong conductive bond. There's two key components, solder and heat. Solder is a flexible metal alloy with a low melting point. There's a few different types, but the biggest differentiator is whether your solder is lead-free or not. Leaded solder is a lot easier to work with, but it's also toxic. However, it is safe to use as long as you wash your hands thoroughly after handling it. Lead-free solder is non-toxic, but it requires a higher temperature iron to get good solder joins. The heat comes from the soldering iron. A soldering iron is a pencil-like tool whose tip can heat up to 800 degrees Fahrenheit. At this temperature, the solder will melt, flowing into the joint like a liquid, forming the bond and fusing the two elements together. There's plenty of different types of soldering irons. If you can get your hands on a digital station like this one, you'll be able to have really fine control over the temperature of the iron. But if you're just starting out, don't be afraid to use one of these simple types of irons. They do a great job too. There's no better way to learn to solder than to splice two wires together. I have my workspace prepared by holding both ends of the wire in a tool called Helping Hands. The two wire ends are twisted together in preparation for the solder, and I already have a piece of shrink tubing ready to protect the joint once it's made. Prepare the iron for soldering by first cleaning it. You can either use a damp sponge or one of these brass coils. Then, melt a tiny amount of solder onto the tip of the iron. This is called tinning and will help the heat transfer from the soldering iron into the solder joint. Hold the iron underneath the wire joint, gently pressing against it. You want the heat of the iron to transfer into the wire ends. After a few seconds, touch the solder into the joint, letting it melt, fusing the two wire ends together. Once the solder cools, you can protect and insulate the splice with the shrink tubing. Soldering components onto a PCB is a very similar process. Insert the component into your board, sliding the wire legs through the holes. Bend the legs outward so the component doesn't fall out when you flip the board over. Touch the iron to the component leg and the solder pad simultaneously so they both heat up. With a clean and tinned iron, it should only take 2 to 3 seconds. Touch the solder to the other side of the component leg and wait for the solder to melt into the joint. Make sure the solder is actually bonding the leg to the solder pad. Sometimes it forms a ball like this, and is called a cold solder. Electronic connections like this will be weak and extremely temperamental. Once you have a good join, trim off the excess with a pair of flush cutters. Clean and retin the iron every few connections you make. Dirty tools make for bad solder connections.
We just seen the video how to do soldering. That video was quite informative. I hope you get the idea how to solder. But when you are working with soldering iron, you must be cautious. If you don't be cautious, then there will be some accidents, and we just hope and pray that doesn't happen. So what you shouldn't do when you are working with soldering irons. Let's see another video.
The skin here is quite sensitive to temperature, and you can tell the temperature quite accurately. It's almost finished now. Just need another piece of wire. Oh sh**! What did I do?
What the f*** did you do?
I'm fine, thanks.
Idiot.
What? I can't even play music from it.
just watched the video for how to solder your circuit. But one thing, try to keep in your mind that consistency is very important. When you are soldering, try to solder everything in the same way. Don't change your techniques and whatever method you use continuously. And for the second video you watch, don't do that. Okay, always be cautious. So as you can see, for the second tools we are going to discuss about is multimeter. You can also call it volt ohm meter. Actually, there are quite few different type of multimeter, but we are just going to discuss this basic one. So as you can see, there is a screen. Then we have voltage, AC voltage, you have DC voltage, and also ampere meter. But when you are measuring ampere, you can see there's two probe, right? So when you are measuring ampere, you must change the red one, the red probe, from normal to the ammeter terminal. So that's the most basic thing. And there's quite few other things, like the blue dot you see, that one is for diode or resistor. And at the regulator at the middle is to change between different mode than what you want to measure. That's why it's called multimeter. You can measure different things in just this one device. And one thing and another thing that we electronics student use most for the multimeter, like previously you learn how to solder, but for this one, when you finish soldering, sometimes we make soldering line, like there's quite few components in one line. So if you want to check that all the components are soldered correctly, there is another sign you can see on the multimeter. It's called continuity beeper. So what this one do, if you turn the regulator in continuity beeper, you touch one probe to one end of your soldering, and then use another probe to check that all the components are aligned in the same line or not. So if there is a beep, then it's yes, your components is perfectly soldered. But if there isn't any beep or no sound, that means remove your soldering with desoldering pump and solder again. That's that's a bad news for you. So now we are going to talk about electronics components and circuit introduction. For basic circuit theory, there are, I already told you it's basic circuit theory. So there are quite some basic things that we already know, like charge, current. Current is the rate of charge that flow over time. And we also know that voltage is potential difference between 2 points of a circuit. So beside that, one of the most important theory of electronics is Ohm's law, obviously. So Ohm's law is stated such a way, like voltage across resistor is directly proportional to the current through resistor. So what does it really mean, and how to calculate V equal IR? What is this V equal IR relation? So let's watch this video.
So what is Ohm's law? Ohm's law is a relationship between voltage, current and resistance and how they relate to each other. Ohm's law was developed by a German physicist named George Ohm, who undertook many experiments to develop his theory, including measuring current by touching live electrical circuits to see how much it hurt. As you might imagine, the higher the current, the more it hurt. Now there are 3 formulas we need to use for Ohm's law, but we don't actually need to remember these, and I'll show you a super easy tip in just a moment. So the 3 formulas we use for Ohm's law are voltage equals current multiplied by resistance, current equals voltage divided by resistance, and resistance equals voltage divided by current. If that seems like a lot to remember, then don't worry, because we don't need to remember them. All you need to remember is Ohm's triangle, which looks like this. So you just need to remember these three letters in order, V, I, R. Then we just write those letters in a triangle with V at the top, and we draw a line to separate the letters. Now all we do when we need to use a formula is cover up the letter we need. So if we want to find the voltage, then we write V equals, and then we cover up the V in the triangle. That leaves us with I and R. So we write I multiplied by R, which means voltage equals current multiplied by resistance. You can write a little multiplication symbol in the triangle between the two letters if it helps you. Now I know what you're thinking, why is current represented with the letter I and not a C for current, or even a letter A for the unit of ampere? Well, the unit of current is the ampere, or the amp, and this is named after André Ampère, a French physicist. A couple of hundred years ago, he undertook lots of experiments, many involved varying the amount of electrical current. So he called this intensity du current, or the intensity of current. So when he published his work, they took the letter I and it became standard until this day. Now you might also come across formulas where the letter E is used instead of V. The letter E stands for EMF, or electromotive force, but don't worry about that. Just stick to using V and substitute V for E if you see it used in Ohm's law questions. Anyway, so by covering V, we get voltage equals current multiplied by resistance. If we want to find current, then we write down I equals, and then we cover up the letter I in the triangle. That gives us V and R. So as V is above the R like a fraction, we can write V divided by R. Therefore, current is equal to voltage divided by resistance. If we want to find resistance, then we write down R equals, and then we cover up R in the triangle. That leaves us with V and I, so we write V divided by I, which gives us resistance equals voltage divided by current. Let's look at some examples for how to use these formulas. First, let's see how we find voltage and how it relates to the other parts. Let's say we have a simple electrical circuit with a battery and a resistor. We don't know what the voltage of the battery is though. The resistor is 3 ohms, and when we connect a multimeter into the circuit, we see that we get a reading of 2 amps of current. We want to find the voltage, so using Ohm's triangle, we can cover up the V, and that gives us V equals I multiplied by R. We know the current is 2 amps, so we can write that in, and we know the resistance is 3 ohms, so we can write that in also. Therefore, 2 amps multiplied by 3 ohms gives us 6 volts. The battery is therefore 6 volts. Coming back to the circuit, if we now double the voltage by connecting 2 6-volt batteries in series, we get 12 volts. If we now connect this to the same circuit, the current also doubles from 2 amps to 4 amps. If we double the voltage again to 24 volts, the current will also double to 8 amps. So what's the relationship here? We can see that current is therefore directly proportional to voltage. If we double the voltage, we double the current. Remember, voltage is like pressure, is the pushing force in the circuit. It pushes the electrons around the wires, and we place things like lamps in the way of these electrons so that they have to flow through these, and that causes the lamp to light up. By doubling the voltage, we see that the current also doubles, meaning that more electrons are flowing, and this occurs as we apply more pressure or more voltage. This is just like if we were to use a bigger water pump, then more water will flow. Okay, so what about finding current? Let's say we now have a 3 ohm lamp connected to a 6 volt power supply. To find the current, we write down I equals, and then we cover up I in the triangle. That gives us V divided by R, so current equals voltage divided by resistance. We know the voltage is 6 volts and the resistance is 3 ohms, so the current is therefore 2 amps, and that's what we see on the multimeter. So we saw what happens when we use a resistance of 3 ohms in the circuit. But if we double the resistance to 6 ohms by placing another 3 ohm lamp into the circuit, the current halves to just 1 amp. If we double the resistance again to 12 ohms, the current will halve again to 0.5 amps. We can visually see this because the lamps will become less bright as the current reduces from the increase in resistance. So what's the relationship here? We can see that the current is inversely proportional to the resistance. When we double the resistance, the current will decrease by half. If we halve the resistance, the current will double. Current is the flow of electrons, or the flow of free electrons. For us to make this lamp shine, we need to push electrons through it. How do we do that? We apply a voltage across the two ends. The voltage will push the electrons. The atoms inside the copper wire have free electrons in their valence shell, which means they can very easily move to other copper atoms. They will naturally move to other atoms by themselves, but this will be in random directions, which is of no use to us. For the lamp to turn on, we need lots of electrons to flow in the same direction. When we connect a voltage source, we use the pressure of the battery to push the electrons through the circuit all in the same direction. For example, to power this 1.5 ohm resistive lamp with a 1.5 volt battery requires 1 amp of current. This is equal to 6,242 quadrillion electrons passing from the battery and through the lamp every second. And if it can achieve this, then the lamp will stay at full brightness. If the voltage or current reduces or the resistance of the circuit increases, then the lamp will become dimmer. Okay, now let's look at finding resistance. Say we have a resistive lamp connected to a 12 volt power supply. We don't know how much resistance is adding to the circuit, but we measure the current as 0.5 amps. To find the resistance, we write down R equals, and then we cover up the R in the triangle. We're left with V and I, so resistance equals voltage divided by current. We know the voltage is 12 volts and the current is 0.5 amps. So 12 divided by 0.5 gives us 24 ohms of resistance. Resistance is the opposition to the flow of electrons. It tries to prevent electrons from flowing. That's why we use resistors in circuits to reduce the current and protect components such as an LED. If we try to connect an LED directly to a 9 volt battery, it will blow out because the voltage and the current are too high. But when we add a resistor into the circuit, then these are reduced, so the LED is protected and will shine brightly. So given the circuit, we can increase the current by increasing the voltage, or we can also increase the current by reducing the resistance. We can also reduce the current by increasing the resistance. Okay.
I hope from the video you already get the idea for Ohm's law. When we are watching the video, we heard the word resistance or resistor. So now the picture you are seeing in the slide, this is the resistor. Actually, more specifically, this picture is fixed resistor. In the module, you can see the other pictures for different types of resistor. The main job for this resistor is to implement circuit resistance in a circuit. But have you ever wondered what this color band means in this resistor? So for that, these color bands actually are given to make us understand what's the value for this resistor. So as you can see, there are 4 bands in this resistor, but when you go to a electric component shop, you can find 6 band, 5 band, even 3 band beside this 4 band resistor. But you will learn better over time. But for now, this 4 band standard resistor, the first and second band, like here in the picture, the red first 2 red bands, these 2 is for first and second digit. Then the brown band here is for multiplier, and at the very end the gold band, this one is for tolerance. I mean, there will be some errors. In more cases we call this tolerance because it's not the error. It sometimes it differs from one like 5% measurement values. So like the first red, if you can see the slide, you see the red is 2. So first 2 band is 2 2. So we have the first 2 digit 2 and 2, and then we have multiplier is brown, that means multiply by 10. So we got 220, and then this is a gold band, so the tolerance is 5%. So the value of this resistor is 220 ohm, but the tolerance is 5%. That means it might be less than 5% less than 220, or maybe 5% more than 220. So that's this tolerance for the module you got for electronics. In the resistor section below, you can see there are 4 exercises. I hope you will practice those 4. Now, when these resistors are in circuits, sometimes you will find that there are 3 or 4 resistors connected one after another, like in series. That's called series, just like in the picture. And sometimes you will find the second case where the resistors are connected parallelly with one another. So how to calculate the total value of this resistor? So for the series one, it's quite straightforward. You just add all those numbers together and you will find the value. For the parallel one, as you can see the formula, you just use this, but there is explanation how we get these formulas, but we don't have much time to explain that in this session. Maybe if you are that interested, you can contact me or any of the Jazarians. Anyone will love to help you. So our next component is LED. So the full meaning is light emitting diode. Yeah, it's a diode. So it's based on semiconductor. If you try to focus, you can see there's in the middle of the first picture, it says semiconductor die. So how this LED works is when you connect this LED with a battery, then electron flows from the negative side to the semiconductor die and goes to the other side. So during this process, electrons fill up the electron holes in semiconductor die, and then that emits energy. So that energy got released as electromagnetic wave, and based on the wavelength, it might be visible light, it might be infrared, it might be ultraviolet. That depends on what type of dye we are using in the LED. Not we are using, it's factory made, so we don't have anything to do inside. The next one is diode. So diode is also a semiconductor device, and it helps to flow current in only one direction. But how does this diode do that? So what's inside this diode? Let's see.
Diodes have numerous applications across the electronic industry, and they are an integral part of any electronic device. In this video, we will explore the inner workings and applications of the diode in great detail. Basically, a diode is a one-way valve for electricity. Let's take a look at the internal structure of a diode. The diode is made of a semiconductor such as silicon. Pure silicon does not have any free electrons, but the silicon used here is not pure. One part is doped with N-type impurity and the other part is doped with P-type impurity. So, at the N side of the diode, we will have free electrons, and at the P side, we will have vacant positions for electrons. Something very interesting happens at the P-N junction of the diode. The abundant electrons on the N side have a natural tendency to migrate to the holes that are available on the P side. So, the P side boundary is slightly negatively charged, and the N side boundary is slightly positively charged. You can see the depletion region that is created. The resulting electric field will oppose any further natural migration of electrons. In short, it builds a potential barrier for electron flow. If you apply an external power source across the diode as shown, the power source will attract the electrons and holes. Electricity flow is impossible in this case. This condition is known as reverse bias of the diode. You can see that the width of the depletion region increases here. However, if you connect positive terminal of the power source to the P side of the diode, the situation is quite different. Assume that the power source has enough voltage to overcome the barrier potential. You can immediately see that the electrons will be pushed away by the negative terminal. When the electrons cross the potential barrier, they will be drained of energy and will easily occupy the holes in the P region. But due to the attraction of the positive terminal, these electrons can now jump to the holes nearby in the P region and flow through the external circuit. This is known as the forward biasing of a diode. Simply put, a diode acts like a one-way valve for the flow of electricity. Now, let's vary the input voltage and study the diode's response to it. In reverse voltage, as explained, you can observe a negligible electricity flow. In the forward condition up to 0.7 volt, you will find a negligible electricity flow. But right after crossing this barrier potential value, there will be a steep increase in the current flow. However, you can note that voltage across the diode does not go much higher than 0.7 volts, even with high input voltage. This is due to in-forward biased condition. The diode offers very low resistance against the current flow. At the reverse biased side, applying a very high voltage will damage normal diodes and result in a high current flow. The one-way electricity flow that is characteristic of the diode leads to interesting applications like a bridge rectifier. During the positive half, the circuit will conduct as shown. The other two diodes will be in a reversed biased state. During the negative half, the reverse will be the case. So we will get the same current flow direction at the output. We can further smooth this output by introducing a capacitive filter and regulator.
As you have seen in the video, diode doesn't only work as a one-way switch but also works as a rectifier. This transistor is almost as same as diode, but instead of only one P region and one N region, this transistor have either two P region, one N region, or two N region, one P region. So let's see how this works.
The invention of transistors revolutionized human civilization like no other technology. At the heart of a smartphone lies a processor, and this processor holds about 2 billion transistors. What do these incredibly tiny devices do? How do they work? Transistors can act like a switch with no moving parts. They can amplify a weak signal. In fact, amplification is the basic function of a transistor. First, let's understand the basis of transistors. We will come back to the application part later. Transistors are made of semiconductors such as silicon. Each silicon atom is bonded with 4 neighboring silicon atoms. Silicon has 4 electrons in its valence shell. Let's replace this silicon atom with a 4-handed smiley. Each hand holds 1 electron. Each one of these electrons goes for sharing with a neighboring silicon atom. This is known as a covalent bond. Currently, the electrons are in their valence band. If the pure silicon has to conduct electricity, the electrons have to absorb some energy and become free electrons. Thus, the pure silicon will have a low electrical conductivity. A technique called doping is used to improve the conductivity of semiconductors. For example, say you inject phosphorus with 5 valence electrons. Here, 1 electron will be free to move in the system. This is known as N-type doping. On the other hand, if you inject boron with 3 valence electrons, there will be a vacant position for an electron. This vacant position is known as a hole, and a neighboring electron can fill this hole at any time. This electron movement is visualized as holes moving in opposite direction. We call this p-type doping. If you dope a silicon wafer in the following manner, a transistor is born. But if you really want to understand how a transistor works, we have to get a clear idea of what happens at the electron level of a more basic component, a diode. Now, back to the transistor. Note that the P layer is really thin and lightly doped. You can easily see that the transistor is essentially 2 diodes sandwiched back to back. So, whichever way you connect the power source, one diode will always be reverse biased and block the electricity flow. This means the transistor is in the off state. Now, let's connect a second power supply as shown. The power supply should have enough voltage to overcome the potential barrier. So, this is just a forward biased diode. Thus, a high number of electrons will be emitted from the N region. Just like in a diode, a few electrons will combine with the holes and jump across the neighboring holes and flow to the base. But there are a lot more electrons that has crossed to the P side. What will these remaining electrons do? Think for a moment. The remaining electrons will get attracted by the positive terminal of the first power source and will flow straight as shown. Note that the P region is very narrow, which ensures that no remaining electrons flow to the positive terminal of the second power source. In short, a small base current is amplified to a high collector current. You can easily correlate the naming of the transistor terminal with the nature of electron flow. If you can increase the base current, the collector current will increase proportionally. This is a clear case of current amplification. The kind of transistor we have discussed is called a bipolar junction transistor. Let's replace this representative transistor with a realistic one. You can further improve the amplification by introducing one more transistor. The base of this transistor is connected with the emitter of the first transistor. If you introduce a weak fluctuating signal at the input, like what you would find in a microphone, you will get an amplified signal at the loudspeaker. The other interesting thing you can note about this basic circuit is that depending on the value of the applied voltage, the transistor can be either on or off. Here, the transistor acts as a switch. This
tiny component you are seeing here is a capacitor. So this capacitor is more like a fully charged battery. It can it charges first and then discharge, but the difference is the charging and discharging rate is much higher than our typical batteries. Imagine you have a LED light with a switch. So if you continuously on and off the switch, you will see a little flash in the LED. But if you put a capacitor in the circuit and then you turn on and off the switch, you won't see any flash. The light will give you, the LED will give you light continuously. So that's why we use capacitor. More briefly,
a capacitor is similar to a battery in that both store electrical energy, but a capacitor is a much simpler device that can't produce new electrons. It only stores them. However, capacitors can do things a battery can't, as we will show here. For the purposes of this animation, we'll focus on different parts of the current propagating through the wires at different times. When we close the switch, electricity immediately runs throughout the circuit. Although the convention is to think of electrical current as moving from positive to negative, electrons actually move from negative to positive, as we represent here with yellow particles. As you can see, the battery is not much good at powering this motor to lift this weight, because it discharges gradually, much more slowly than would a capacitor with the same charge. Here we'll learn why a capacitor is much better suited to such a task than a battery. Like a battery, a capacitor has two terminals, positive and negative. Inside the capacitor, the terminals connect to two metal plates separated by an insulator that keeps the plates from touching each other and allows them to hold opposite charges, maintaining an electric field. Capacitors can be useful for storing and quickly discharging electricity, so you can power, for example, an electric motor as we'll show here. First, we need to charge the capacitor. By closing the switch, we create a circuit that includes both the capacitor and the battery. Electrons flow from the battery to the capacitor, where they are stored. Here, a yellow glow represents the increasing charge held by the plate. For every electron gained by that negative plate, an electron is lost by the positive plate, maintaining the capacitor in equilibrium. Here, the red glow represents the positive charge held by the plate that increases with each parting electron. The capacitor continues to charge until it attains the voltage of the battery charging it. Now that the capacitor is fully charged, let's put all that stored energy to use. By connecting it to a new circuit, we can power a small motor. This electrical current powers the pulley to lift the weight until the charge dissipates. The electrons on the capacitor's negative terminal are drawn to its positive terminal. They rush along the path that leads there, straight through the motor. Let's watch this again. Even though the battery and the capacitor attempted this task with the same amount of charge, only the capacitor successfully powers the motor lifting the weight because it discharges much more quickly. This feature makes capacitors useful for powering things that need a quick surge of energy, such as flash bulbs and cameras, and starter motors and audio amplifiers in your car.
After capacitor, we have this component potentiometer. We call it potentiometer, it's just like variable resistor. As in the slide, you can see at the top we have a knob, it's called knob, and at the bottom we have three terminals, and the round shaped body, it's the resistive element. Its working principle is based on the length of resistive wires. In the next slide, this slide, if you focus, you can see the A, B, C are noted in the terminals. So, and the knob, you can actually turn the knob either in clockwise or anti-clockwise. So, if you turn the knob clockwise, the resistance for our AB terminal will be higher than BC terminal. But if you turn it anti-clockwise, the resistance for BC terminal will be much higher than AB terminal. So, and by using this, we can actually regulate voltage, frequency, speed for cars. Like after this session, or if you want to make a remote where you want to maintain the speed of a autonomous car, you can make it by using this. This earlier is another type of variable resistor. Actually, this variable resistor is nothing like potentiometer. You can't turn the knob right or left, or you can't slide anything. This variable resistor is already factory made, so there is nothing you can change. Actually, this variable resistor changes with the intensity of light. So if the intensity of light increases, then the resistance of this component falls. So actually, for a typical LDR, during daylight the resistance is around 5,000 ohm, but during dark it's more than 2 million ohm. You can imagine, if there is 2 million ohm resistance, then no current will flow through this LDR. So sometimes, most of the time, we use LDR as a switch that is based on lights. Now, this component is most important and most interesting. We all heard the name IC, so this is integrated circuit. But why is this called integrated circuit? Because there are thousands of circuits, small circuits built in just this small component. Can you believe it? So okay, so we can just see what's inside this. So now this slide, you can see actually what's inside the IC. We just remove the front layer and this circuit is here, but this is not only like this is not just the circuit. If you zoom in into this using electron microscope, you will see millions of circuit. We are going to watch that together. As you seen in the video, in the IC there are thousands of circuits, and so using these thousands of circuits, some ICs are fixed for doing some fixed works, like they are previously programmed such as that, or there are other ICs that you can program yourself. That's called PIC, programmable IC. That's all the basic components we are going to learn today. But if you merge these components with some advanced components and make a circuit for whatever purpose you need, that's what we call sensors or modules. So now we are going to discuss about some sensor. So the first one is infrared sensor. This is an infrared sensor. Usually we use infrared sensor for detecting any of the objects. So we have one infrared LED that's emit infrared, and another one detects the infrared light. Let's connect the infrared sensor with Arduino. As you can see, we connect VCC to 5 volts, then GND of the sensor to ground of Arduino, and output to analog pin. Any analog pin you can connect. It doesn't have to be 0. So about the emission, it's emit infrared spectrum that's without any obstacle doesn't come back. But if you put an obstacle, the infrared light will bounce back to the detector. But you have to keep one thing in mind, that if the obstacle is white, then the whole infrared will come back after reflection. But if the obstacle is black, then nothing will come back, because black color absorb all forms of light. So that's all for infrared. By using this technique, this method, you can detect a white or black line. There are various types of sonar sensors, but all of them works in same principle, just like a bat that produce sound first, and when that sound wave hits something and came back echoing, then they receive that sound and find the path. Sonar sensor works in the same way. In the sonar sensor, there is a transducer that produces sounds in a fixed frequency, whatever frequency you want. So as in the video, you are seeing the the orange wave. That is the produced sound by the transducer. And when that sound is bounced in any of the object and come back, there is another receiver that receives the sounds. Then calculate using normal formulas to find the distance. Not only distance, actually sonar sensor, by using advanced sonar sensor you can determine the shape and also the materials of object. Even if you use two or three sonar sensors simultaneously, you can find and visualize exact shape of one object. And that's what we do with sonar sensor when we are making any projects or something like that. Next, we have proximity sensor. Proximity sensor is another sensor just like infrared and sonar sensor that can sense the presence of any object. But for proximity sensor, it doesn't only use either sound wave or infrared. Proximity sensor use varieties of different techniques or different laws, theories to detect the presence of any object.
Proximity sensor is a sensor able to detect the presence of nearby objects without any physical contact. A proximity sensor often emits an electromagnetic field or a beam of electromagnetic radiation, infrared for instance, and looks for changes in the field or return signal. The object being sensed is often referred to as the proximity sensor's target. Depending on the proximity sensor targets, different sensors may be used. For example, an inductive proximity sensor requires a metal target, whereas a capacitive photoelectric sensor may be suitable for a plastic target. Proximity sensors have a long functional life and high reliability due to the absence of mechanical parts and the lack of physical contact between the sensor and the target. A proximity sensor that is adjusted to a very short range can often be used as a touch switch. Proximity sensors are commonly used in industrial applications, from manufacturing and food production to recycling. They are also used in vehicles for detecting the proximity of other vehicles relative to one's own car, as well as for parking assist functions. In mobile devices, especially phones, the proximity sensor is used to detect whether a user's face is close to the phone during a phone call, prompting the screen.
Now we have is temperature sensor. For temperature sensor, actually you are using temperature sensor even if you didn't notice. Like you have temperature sensor in your phone to detect the temperature if your phone is overheating or not. They are in cars. Even when you feel sick and want to measure if you have fever or not, you use thermometer. Thermometer is also the basic version of temperature sensor. So how this temperature sensor works is actually they try to measure the change of elements for basic, like when you are using a thermometer, it's use mercury and measure the change in the volume to measure the temperature. There are other other components like thermistor to measure temperature, which use resistance to measure temperature, and many more.
Generally, a sensor or transducer is a physical device which is capable of transforming one type of process variable to my favorite signal type. To elaborate on this generalized sentence, let me give you an example. Temperature, pressure, flow, etc. are some process variables, and actually, they are physical characteristics of our real world. With modern technology, and because of tremendous advances in electrical engineering in the past century, we like to transform every measurable process value into an electrical signal, and a temperature sensor is a device which will transform the temperature into an electrical signal, no matter how tiny the amount of this signal might be. So far, I took a big first step, which was the transformation of temperature into electrical signal. Based on different sensor technologies, this signal may have different ranges, and for industrial applications, I need to have my signals limited to some universally accepted electrical signal ranges. Today, some of these globally accepted electrical signal ranges are 4 to 20 milliamps, 1 to 5 volts, 0 to 10 volts, etc.
One of the most basic way for short-range wireless communication is Bluetooth. We use Bluetooth every day, everywhere. From your smartphone, your smartwatch, or even cars, all have Bluetooth. We play music using Bluetooth speaker, or we play games using Bluetooth mouse. And for our electronics part, we use Bluetooth module for making autonomous wireless communication. So how this Bluetooth works? What is actually Bluetooth is?
Bluetooth is the prime wireless technology used across virtually all devices. Bluetooth is just an invisible wire that connects different devices together. And hang with me here, we're going to get more complex as we keep moving. When we say Bluetooth, we really mean the connectivity between devices, because this involves both a signal and some hardware. On the hardware side, both devices need to be equipped with an antenna-supplied chip that can encode, decode, and transmit data via an antenna. We all have probably tried and hopefully succeeded at connecting a device through Bluetooth. What's really going on is the device that is set to be discoverable, usually the one with the final output, like a speaker, sends out pinging signals that can be detected by other Bluetooth-enabled devices. In other words, it shows up on your phone screen. Once you hit connect and link the devices together, you've just formed a PicoNet. No, this isn't a net used to catch yellow Pokemon. Pikachu net. Okay. This is actually a micronetwork of recognizable radio waves communicating back and forth between devices. These waves are short, about 15 meters, so that there aren't conflicting Bluetooth waves all over the place. The signal itself operates within a frequency of 2.4 to 2.485 gigahertz, which falls in the unlicensed scientific, industrial, and medical category. To continue down the path to technical understanding, according to the Bluetooth website, it uses a spread spectrum frequency hopping full duplex signal at a nominal rate of 1600 hops per second. To break that down into words that just about everyone can understand, the signal isn't just on one frequency. In fact, it hops around to all different frequencies. A lot. About 1600 times per second to be exact.
The Bluetooth module we use, AC05 or AC06, establish a serial port protocol using this Bluetooth to build up a communication between different physical projects without any wires. And this AC05 and AC06 also can switch mode from master to slave. So this one single module can be used as a master signal producer or signal receiver. So that means you can use only two Bluetooth module, and you can make two masters or two slave. That way you can control any of the projects you made wirelessly with another one. Now you're going to learn the most important part of this whole session, Arduino. The three pictures you can see in the slides, these are Arduino. Besides these three, there are quite few other Arduinos, because Arduino is an open source board, so you can even make one of your own design. But what is actually this Arduino? For Arduino, Arduino is a microcontroller based developed board, and microcontroller is a small IC or microcontroller. That means it can control, in layman word you can say it's a robot brain. Even before this Arduino, we engineers used to use microcontroller directly, but that is so troublesome, because if you are using one main microcontroller, then you are going to connect all your components with that microcontroller. Then you need another microcontroller to program the one you are using, the main one you are using for the project, to program it. Then even there were risks that sometime when you program a microcontroller, the microcontroller can burn. So and this might get expensive sometimes. So some of the early scientists, early engineers, they developed a board that can make things easy. But those boards are so expensive. So early of this decade, one of Italian engineers team, they developed this Arduino to make everything easy to use for beginners like us. And that is how this Arduino created. So let's hear from the founder and the inventor of Arduino.
So my name is Massimo Banzi. I'm the co-founder of the Arduino project. At the moment, my main job is to be the CEO of Arduino, but then I still do some teaching to keep connected with reality. When we started, there was no concept of makers. There wasn't this awareness of a maker movement. So our first community was designers, also the people that studied the same subject as my students. So a lot of people made cool projects, share them online. It's not about showing the pictures of the circuit, which is, the engineers, they're excited about technical qualities of a project, while the designer is more interested in the human being. He or she will make a project and try to communicate it to as many people as possible. Say, this is an object that's going to solve this and this problem, and then the technology is less relevant. And then it kind of spilled out of sort of the art and design and music into people just doing their DIY stuff. So in a way, the open source hardware movement and the maker movement in general, they are influencing education already, because they make a large quantity of information available for free, written sometimes in a language which is more understandable than the classic way to explain what electricity is, but more human-friendly. So in every school, there's always that teacher that tries to experiment, that tries to go one step, beyond. And those people, they can show the others, look, I've done this and I tapped into this community and we made this amazing thing, why don't you? And they pull the others in. So it enables these people to be awesome in a way.
We just listened Massimo Banzi talking about Arduino and the maker movement. And we also saw the video how Arduinos are made in the factory. And all in these Arduinos, Arduino Uno is the most basic one. In this slide, you can see all the configurations and pinouts and components that Arduino Uno use. This is quite long, but we are not going to discuss this one. Instead, we are going to discuss a much simpler one. So here you can see in the power, for the power we have barrel jack and also USB. So you can either power up the Arduino with a barrel jack or a USB. But the power limitation is for Uno is up to 20 volt, but the safest is 12 volt. Then we at the right side we have reset, and then we have power out. For reset, if you connect the reset with ground, then if there was any previous code or programming in the Arduino, this connecting reset with ground will format your Arduino, so it will be a clean slate. Then we have power out. It's 3.3 volt and 5 volt. For power out, the power up you use either in barrel jack or USB. you can actually use power out 3.3 volt or 5 volt to power up any other sensors you are using. Then we have ground. Actually, if you see in your module, you can see in Arduino Uno there are actually 3 ground, but you don't need to worry, all 3 ground are connected internally. And then we have power in. Now this power in is another way to power up your Arduino. So beside barrel jack and USB, you also can use this pin to power up your Arduino, but barrel jack and USB can handle much higher power, and so when you are certain that your power is optimal for your Arduino, then you use this pin to power up your Arduino. Then at the bottom we have A0 to A5, 6 analog pins. What do I mean by analog pins? So these pins are for input and also output. These pins can vary from 0 to 255. Suppose you have 5 volt, so you can 5 volt input, so you can divide this 5 volt input from 0 to 255. Unlike the other side, you have digital pins which can only take input 0 and 1, which means either there is high input or low input, so or high output or low output. But the interesting fact about these analog pins that Arduino Uno has already built in ADC, analog to digital converter, so you can use these analog pins as digital with much more accuracy. Then at the top of left side we have a ref or reference pin. So actually this pin is for when you are comparing your input voltage with some external voltage. So you just take that internal voltage and put it in a reference, and then you can compare any of your input voltage with that reference. Then below reference pin you have ground again, and then from 13 to 2 is the digital pin. But you need to notice that beside some of digital pins there are a wave sign, something like that. So this wave sign means it's PWM, pulse width modulation. If you want to know more about PWM, you can search online. And then we have RX and TX pin 0 and 1. This RX and TX is important for programming in this Arduino and also making serial communication with any other device such as sonar sensor or Bluetooth module. You can program Arduino either using USB or using these 2 pins. And at the end you have a reset button, as you can see. So this reset button is just to reset every time your Arduino. So this is the basic Arduino Uno, but in future we are going to use maybe Arduino Nano for compact design, because Arduino Nano is so small and the pin configuration is just the layout is different, but you will find similar pins like analog input output, digital input output, power sub, ground, RxTX, everything, but the layout will be different. Same goes for Arduino Mega. Mega is for big project and it also can handle a lot of powers. And now if you again look at the picture, the big black one is the main microcontroller, and this Arduino doesn't only have one microcontroller but two microcontrollers. The main one is Atmega, but there is another one, the small one, right below the USB power in. That one is for converting the USB to serial communication. This slide is for you to gain more information on Arduino Uno. As you can see, the microcontroller model is Atmega 328P, and the operating voltage is 5 volt, input voltage 7 to 12 volt, and the input voltage limit is 6 to 20 volt. So what does that mean? So operating voltage 5 volt means the components inside that board is going to operate in 5 volt, the Arduino itself. But then you may ask, then why we are supplying 7 to 12 volt? Because the Arduino already have a voltage regulator built inside, so there won't be any problem even if you give voltage higher than 12 volt, unless you put more than 20 volt, because 20 volt is the limit. If you supply more than 20 volt, you might damage the Arduino. Then for digital input output pins, if there are 14 digital input output pins, then and 6 of them are PWM, then analog pins are 6, just as we seen earlier, A0 to A5. And we have flash memory of 32 kilobyte, SRAM 2 kilobyte, EEPROM 1 kilobyte. These are just you can find in the datasheet with the Arduino when you bought it. So besides this Arduino Uno, as I mentioned earlier, we are going to use Arduino Nano, but I want to let you know that during our later on, when we are going to prepare for our robotics game, we are going to use Mecha Nano. It's a slightly advanced version than Arduino Uno or Arduino Nano. It's a compact developed board with some interesting features built in itself, and this one is from Citron. So, and this slide, there are other boards in the market beside Arduino. Some famous one is Raspberry Pi, Latte Panda, and others. Raspberry Pi is not like Arduino. Arduino is so basic, it's only based on microcontroller, but our Raspberry Pi is based on both microcontroller and microprocessor. Actually, Raspberry Pi is a computer itself. Even if you just use a screen, you can use the Raspberry Pi as a Linux computer. Same goes for Latte Panda and other single board computer. So that's the theory for Arduino. The next we are going to know more in the hands-on session. But before hands-on session, if you have any questions, just ask me anything about this in the Q&A session. For Q&A session, again, I'm going to give you a code for menti.com. Put your question there, and after the Q&A session, we are going to have a quiz, and this quiz is going to be fun. You will be rewarded if you win this quiz. For first prize is a multimeter, and the second prize is a soldering iron. The more details will be coming soon.